That's right, boy. All right, so let's start with magnets. Someone ready? Right. Magnets have two poles, north and south. Magnetic fields leave the north and go into the south, right? That's okay? Right? In order for us to find the direction, remember, we could use a simple plotting compass, right? And the plotting compass will give us direction. Right? Right. What you will recognize is that whenever you're close to the magnet, like here, right? Where is the magnetic force strongest? Close to the magnet or far away? Close, right? If you look here, if I draw a circle here, and I draw a circle here, right? What's the amount of field lines per unit area compared to here and here? Here's more and here's less, right?
Yeah.
So here, we have something called high magnetic what?
Plus.
Very good. High magnetic flux. Right? That's the amount of field lines per unit area. Here we have low magnetic flux. Right? There we have low magnetic flux. Right? Nice. So one of the things that we need to remember we have right hand rule and left hand rule and so on. Right. If you remember your Fleming's left hand rule, you might remember that a force is experienced when we have a magnetic field and a conductor. Right? This is Fleming's left hand rule, right? Fleming's left hand rule. Right? So if I take a current carrying conductor and I place it in a magnetic field, I'll experience a force. All right? So you all might remember something like this. You have north and you have south, and you have a current carrying conductor. What does that symbol mean again? In or out?
Out.
And what does this symbol mean? Current going in. Nice. How do I figure out the direction of the force here? How do I figure out the direction of the force? No, still left hand also. Right? Whenever you have a current carrying conductor in a magnetic field, you'll experience a force. You know, the man just watching the screen and wouldn't say, letting the girl. The man just watching the screen now. Right. So if you look here, magnetic field, north to south, current coming out. So the force exerted is where?
Up.
The force exerted is upwards. Here, magnetic field, north to south,
Down. Current
going in. So the force is down. How do we draw the magnetic fields now to get that force? Remember what to do?
Like a spiral.
Like here, no sir. On top here, all the field lines are very close together. And here, you have field lines like that. You have less here, more here. And because you have more on top, it pushes it downward.
I was wondering that, I had a question, 2007, and I was like, I don't know what to do.
You don't know what to do.
Um,
Right here,
I'm not master.
and here is the reverse, right? Right? And it pushes all the way up.
Yeah.
Everybody okay with us? Right? So your field lines look so your force experience looks like that. So, Jacob, what are the things that are affecting the force there? Well, what are the things affecting the force? Right? The magnetic force is affected by what? By what?
By the length of the wire.
By the length of the wire.
The current.
Okay, by the current in it.
Why can't it length?
Length of the wire. Right? Now let's you have current there already. What else? I want to make the force on that larger.
So the strength of the tools.
Right. Right? So I can make the magnetic field stronger, right? So I could say strength of the magnetic field. Right? Is it directly related to all of these things? Is it directly related? Think about it. If I increase the current here, will the force be larger? Yes. If I increase the length of the wire, would the force be larger? Yes. Because I have more in contact with the magnetic field.
Why?
Increasing? Kinda, but that's when you go a little more in depth. Right? But anyway, we'll talk about that later on. Strength of the magnetic field. If I make the magnet stronger, obviously the force will be larger. Right? So from this, oh, by the way, you all remember something special about Fleming's left-hand rule? Something very good. Everything must be 90 degrees. But that does not mean if it's not 90, you don't get force. Right? For example, if these two close in, you'll still experience a force, but it'll be smaller. Right? So something that's important as well is the angle. Between the conductor and the magnetic field. Right? So the angle is important. At maximum when? At maximum at 90. Right? So the formula is F is equal to BIL sine theta. That's the formula to find the force. Remember seeing that? Very good. Very good. That's the formula. It max when it's perfect. Right? When theta is equal to 90 degrees, F is max. Okay? And it becomes F is equal to BIL. Right? So from this, can we make up a definition, Kiran? From this, can we make up a definition for B?
Yeah.
Right? B has to do with the strength of the magnetic field. Right? B is called what? B is called the magnetic flux density. Nice? Right? Force acting per unit current per unit length. So from this, you have a formula for magnetic flux. What's the SI unit? Tesla. Very good. Right? And as we said, the force max when theta is 90, right? Right. But everything here has to do with what? A static conductor, right?
Yeah.
But suppose the conductor moving now. Suppose now we do something like this. Suppose I have a north pole here and a south pole here, magnetic fields here. And I take an electron and I move the electron inside it. Right? I move an electron inside here, right? So I'm moving. Now we're looking at a moving particle.
So is it change when you of density?
No, I'm keeping the magnetic flux, but I'm making it fast. I'm making the conductor move. So instead of a conductor, I'm using an electron. Question number 1. What direction will the electron move in? Well, going that way, but will it go up, down, left, right? Down? What do I use? Yeah, I use a law.
Yeah, it's
Fleming's left-hand rule, right?
So
This is what? In Fleming's left-hand rule. Huh? No, this is field. Current. Current is the direction of what charge?
positive.
Positive. So if a negative charge going this way, positive going towards me. Right? Magnetic field going where? Not to south. North to south. So what you do now? So how will the electron move? Right? Huh? So watch here. Magnetic field not to south. Electron going that way, right? So therefore, what you can say about that? If the electron going this way, then the current direction is towards me. So the force is out. So it's coming out like that. Okay? So it's coming out like that, right? Right, nice. Let's see if we can figure out the force on it. Right, sorry. Right, so here we need to figure out the direction of the force. We know it's 90 degrees, but we need to figure out how to find the force on an electron because it have a force acting, right? Because instead of going like this, it curling out. Right? I can't really draw that, right? That kind of way. I put the draw it the other way around. Right? Any ideas how we could find this force? Let's say it's moving with a velocity v. I want to find the force. I want to find the force exerted on this electron.
Use V over D.
Huh?
V over D.
So we know F is equal to VIL. Where I was saying VV is equal to, since velocity is equal to distance traveled,
Yeah.
right? So let's say the distance traveled, the length here, let's say L on T.
Or BIL, I is equal to QT.
So Q is equal to
IT.
IT.
So I is equal to Q on T.
So I is equal to Q on T.
Is BQL over T, and L over T is V. So B.
So substitute I is equal to Q on T.
And then L on T is V.
So then you can say BQ by L on T. This is
B.
B. So F is equal to BQ.
Yeah.
That's all you get, sir. Right? That's the formula for the force exerted on an electron moving in a magnetic field with a speed. Right? When is this force maximum, Cristiano? When is this force maximum? When the electron is 90 degrees. Right? Because technically, so generally, Cristiano, generally the formula is this. BQB. That's the formula generally. But theta is not. Sorry? Angle between conductor and magnetic field. Send your hand out, by the way.
Excuse.
Electron moving through a magnetic field. With a speed v, yeah. With a speed v. Oh wait, this AC on still? Are you okay with it? Yeah, good. That's not other way. You're done? Alright, you should be down there, right?
I have a question, can you give us a note for B, please? The definition,
Which one?
B,
Yeah, it's in your hand up. I can't show it
Yeah.
out now. In your hand out here. Look at here. Right, magnetic flux density of a magnetic field is defined as the force per unit current exerted in a current carrying conductor which is perpendicular to the magnetic field. But Marquis, remember how to make it simple, right? Force acting per unit current per unit length, right? So you don't necessarily have to remember the exact word I give you. Once you write the formula, put it in words.
So now we know the.
Yeah. Force acting per unit current per unit. Per unit means divided. Right? You're good to go, you're still getting marks. It's not wrong, it's formula in words. The formula not wrong, put the formula in words.
but yeah, I say perpendicular.
Huh?
Yeah, I say perpendicular.
Yeah, you are squeezing that because you're using F is BIL.
Yeah.
Right? If you're using F is BIL sine theta, then you are say that.
So say one more time.
What?
Force acting per unit.
Look at here, force acting per unit current per unit length.
Yes.
Right, nice. And we talked about it moving through a current carrying conduct, a charge moving. We talked about Fleming's left hand rule. Right. The next thing we have to look at, right? Remember, we have, for example, a current carrying conductor has a magnetic field looking like this. Do you remember this? Whose rule is that? Which rule? Right hand grip rule. Right hand grip rule. Try it here now. Right hand grip rule. Thumb pointing upwards. And the fingers point the direction of the magnetic field. Tell them again, Cristiano. Tell them how to use the right hand rule. You must see your tongue. Right. So, question. If you were to find the magnetic field here, it's dependent on current and how far away you go. That's okay? I'll give you the formula in a little while. But here, look at this here. If you have one flat coil, to find the magnetic field strength at any point or magnetic flux density, formula will change slightly, right? Yep, you have to know all of them. And then if you have a solenoid, to find the magnetic field, the formula will change slightly again. Okay? So I want you don't have to draw anything, just write the three different formulae, right? And write what each letter represents. Here, that is for a straight wire, a straight conductor. Right? A long straight conductor. Mu naught is permittivity, I is current, and pusher.
You forget the R.
No, but A, I use it.
Same thing. Why do you use R though?
Because I just use the U.
Yeah, but it makes sense because the yes.
It's not radio, it's distance away.
It's still something.
It's not radio.
Yeah.
Mu naught I over 2 pi A. A is the perpendicular distance from the conductor. Swell one. Permeability here.
Which one is this?
You're done? Next one. All right, missile. So you have three different versions, right? Yeah, next one.
Yeah.
Flat coil. I'll go to what the letters mean just now. Flat coil. Write the formula for flat coil.
What do you want before this platform?
One before the straight conductor, a long straight conductor. Right? You know what I and R are? R is the radius, I is current, and is the number of turns. Right, before forget, right, just write this value down now. Permeability of free space, just write that down, say don't forget, right? It should be -7, eh? It's -7, sorry. Write this down, please. The value for permeability of free space, right?
And that is coming.
Yeah. But I want you to know which one is which. It have permeability and it have permittivity.
Yeah, but how do you use back to the app? And have the view.
Yeah, no, I have to make sure you know which one is which. So when you see the values, when you post the. And last one, solenoid. Right. Notice that for the flat coil, capital N is number of turns in the coil, right? But in the solenoid, the number N is the number of turns per unit length. Okay? Make sure you identify the difference, right? That's mu naught.
So, what's your formula?
Mu naught NL. NI, I mean. N is the number of turns per unit length. Highlight that, please. You remember how to find the direction of the magnetic field?
Oh,
How you find direction of the magnetic field here?
that's all.
Sorry, sir.
That's all. Good. Right, good.
Right, you're using the right hand ruler. How it is good?
So,
Direction, I think.
What direction is the magnetic field there? current going up on the left and down at the bottom.
Then all three page on top and then straight off.
No, what direction is the magnetic field? Yes, it going. Yes, it is going. Yes, it is going in at the top and out at the bottom.
You mean out at top and in the bottom?
No, it's going in at the top, out at the bottom. It's going in here, out the bottom. See that? It's going in at the top and out at the bottom. What's your current doing?
Okay.
See that? What is blue line here? What's this line here, right? What's your red line? It's going in at the top and then coming out at the bottom. In at the top, out at the bottom. Right? So therefore you have X's on top, dots underneath. Right? So you have X's on top, dots underneath. Right, no force. Remember, we're trying to find the magnetic field direction. So, I'm going over. So it's Fleming's the right hand grip rule, yes. But now it's switching everything around. Your fingers point in the direction of the magnetic field. Sorry, your fingers point in the direction of the current, and the thumb points towards magnetic north. Yeah. So your thumb points towards magnetic north. So you're going in at the top, out at the bottom. So your thumb points here. Here is north, here is south. So it's leaving here and it's going in there.
One of the bottom is blue.
I think you are getting something.
So,
You see that?
so.
Alright, I'm going to make a board. I'm going to need board and show you.
You're like, boy. So, right?
Wait, that's all magnets. Like,
Right. In direction.
Like this, right?
so I'm gonna show you.
This is true, right?
So what I'm going to do here, I'm going to erase this. And I'm going to erase this. Right? And when I finish erase it, what I'm going to do here, I'm going to show you what to do. Right, so watch here. So we could use right hand grip rule. Right? We could use the right hand grip rule twice. Right?
Twice.
Right hand grip rule, the first time you can use it is when your thumb points in the direction of the current and your fingers point in the direction of the magnetic field. That's the first time. So for example, if I give you X, X means what? In. So my thumb pointing in and my fingers pointing in a clockwise direction, right? So you use a rule like this if it's a straight conductor. But now when it's a solenoid, for a solenoid, we do it the other way around. For a solenoid, we switch them around. We say that the thumb, let me draw it like this, right? Right? Your thumb now points towards magnetic north, and your fingers point in the direction of the current. Right? So Fleming's, right hand grip rule could be used here or here. Right? If it's a conduct. So the example that we had what on top? Watch this here. If I have current going this way, it's going in at the top and coming out at the bottom. In at the top, out at the bottom. In at the top, out at the bottom. Right? Right? Think of pepper going in at the top and coming out where? Bottom. Right? So it's going right? In at the top and out at the bottom. So we're gonna use the rule now, right? In at the top, outside quarter. Right? So your thumb points towards magnetic. Thumb points towards magnetic. So here is north and here is. So it leaves the north and comes into the south. Leaves the north, comes into the south.
Oh, and who is this?
Huh?
Is this connected to the slope?
No. We rain recharge. Not really. But it's similar to concept of lens law. But when we share it, remember lens law is for generators.
Yeah.
So you apply a force in a magnetic field to get a current. Here we have a current giving us a force. Right? So take us down now. Remember, this is the right hand grip rule. Method 1, method 2. Straight conductor. Right? Straight conductor here. Solenoid. Oh yeah, copy down fast.
Okay.
Right, following remember to sign up in class work.
Yes.
Alright, you're done? Let's try the small calculation here now. Write it down now, please. Wait. Oh, you're watching something. Sorry. Sorry, Faith. Try that, please. Hey, Shiman, try and boy. Hey, wait. How much credit did you last year? 4, 3 or 4, no? What was Cristiano, if you hurry up, please, boy, please. Please, boy, Cristiano, boy.
Alien, Africa.
After this, next thing I'll give you a small break. No, 7.
No, it's still 7, but.
You know, this company late anyway, so it might as well.
Look at the lead time change.
Yeah. Esto sale algo así. ¿Ah? Pero usted. Ah, okay. Lie down with colors tomorrow. Tomorrow, do work fully. Yeah, you'll be about to sit down going. And that was that pizza snack and shit. Pizza dough? What's that?
How much is the deal on here? Oh, 459.
Oh, you want to know now? I tell you. All right, sit down. Okay, tonight, sit down. I said tonight, sit down, please.
459.
No, I can't remember Marcus being so. Hello? Right? Yeah. For the biggest, I don't know. What is that?
No, we didn't play. We finished too late by the time it was my like half three. I read the come up lessons.
Was playing that.
They played you wrong. They're like, yes. There's no demand. Like organize this. No, but check your other that.
That was not there.
But like, right, they would have anybody responsible to try that the was
Nobody. You're done? You're working backwards, right? Oh, yeah.
and somebody gave that in, like you're wrong, that's the idea. They're wrong, that's the
When they played that, well, the 1 to 4, they played already. He really played, but no.
Yeah, I know, exactly. I got one, seven. I'm going to. I find number zero five. Yeah. Oh, by the way, that's next. Yeah. And then, but if they land there, and then that's not do something without it. It's not, you can do that, and if I said yes. I think in that, they both don't know too, would be. You have to divide it by, a multiply by four. Seriously. You have to multiply by something, it's serious. That is a person I have to. So the people in the past. That actually happened. You can choose to go. So I'm saying. What we said, yeah, that's this from this outside. Yeah. It's born to be questioned a lot. What else? Power. Power. Yeah, so okay, they asked.
Sorry, there, earlier. Right, sorry, so let's take a look at this. I give you a break just now, right? That was a break, right? Yeah, that was a break. Right, so they told you the magnetic field is this. They gave you the radius R, and they gave you the length here,
Okay.
and they gave you the current. They want to find the minimum number of turns per unit length. What's the formula we use here, Cristiano? V is equal to what? You know what? NL. NL and I. I say L. It's the same thing, same thing. Sorry, I didn't know what the same thing. I really didn't know. So N is equal to 0.027. I have 0.027 divided by 4 pi by 10 to the minus 7 multiplied by what I was 12. What should I got to N?
1790.
1.
790.
Right? Again, that's the number of turns
Per unit.
per unit length. Nice. Total length of the wire. Ooh, nice. That's like what you have to do now.
Yeah.
So that's the number of turns in 1 meter. Okay? So what to do?
See, I multiply by 40 by 10 minus 2. I get 716.
So you multiply 40 by,
Yeah, by 1790 by 40 by 10 to the minus 2.
right, okay, you convert it, right.
Yeah.
So you multiply 790, that's the number of turns in a meter,
Yeah.
multiply by 0.4,
Yeah.
right? That will give you the number of turns,
716.
716,
6.
that's it?
716, yeah. And then you had a length
Right. So that's the number of turns, you have to find how long is one turn.
So and by 2 pi r.
And by,
2 pi r.
so that's 716 by 2 pi by,
1.4 by 10 minus 2.
where's R? Right, 1.4 by 10 to the minus. How much you get it?
62 meters.
60.
I guess it's true.
Yes, it's true.
I guess it's like.
63, right? But you'll follow what we did. So let's go back here. The first thing we did is we used the formula for magnetic field strength. We use the formula for magnetic field strength for solenoid. That's not. Oh, somebody needs a big marker down. All right, nice. So we found the number of turns per unit length. So for every, what does this say here again, Olia? 1790. What does that say?
That's the number of turns.
That's the number of turns in 1 meter. So since it's 40 centimeters long, we can multiply 40 by 1790 and we'll get the number of turns. And we got 716. Since they have 716 turns, just find the perimeter or the circumference of one turn and multiply by 716. And we got 63 meters.
So what's your point again?
Pardon me?
What's your point for?
Because they told you the length of the wire is 0.4. You okay with that? Yeah? All right. Let's take a look now at you're okay there, right? So we use the formula we rearrange it, right? I want to take a look at this scenario here.
Yes, sir. We are breaking. So
I just give all the break.
When
Run out inside
I
there.
was working out that question.
you just gonna fix it up.
Come on. We can make sure.
Because you never give me no problem. Say, so our question is good.
You need a formula for that.
So
All right. Let's just talk about this for a few seconds and tell me what you all think.
Alright.
Here we have two current carrying conductors. You're seeing that? Around the conductor, there is a what? Magnetic field. So the question is, will this attract or will this be repulsive? Yeah, look at this. One going up and one going down. Oh, we're gonna prove this formula, that's not right. One going up, one going down. Huh?
What we do next time?
I want to know what you all think. Is it repulsive or is it attractive? Did you attract? Take a break and then we'll come back and see if you're right. Right? Your break is 6 minutes long. At 6:20 we started back.
Yeah,
6:20 I am starting back. Very grateful, right? You do your own thing.
Thanks, Ryan.
What?
Do I come back on time?
You are late, sir.
Yeah.
So, are you feeling going?
What? Yeah, I'll show you.
So, but why you feeling magnets? I'm coming.
After we've done everything, then I'll tell you. So, but if I tell you no magnets are coming, you gonna pay attention?
Yeah. You can't need it.
So it's
Wait, that's something. Huh? No, but what is wrong with what I'll tell you. But when the crash wasn't after I'll tell you.
So you gonna.
Now, whatever you say coming, I'm gonna revise the opposite thing now.
Yeah. Yeah.
No, when last year, will I get 2 right? Or 1?
One.
1?
Well, not 6 is not.
I'll take it off. 1 out of 3, boy. Yeah, and the last year was 2. Last year they got 3 up. I never said that.
Yes.
I will never bank on. I thought you
Good,
cover
I study
everything.
everything.
I thought you had to study everything exactly.
Yeah, I'm gonna come like I said. Yeah, right. It's something I gotta leave now, but it's yeah, that's
Alright, so we're going back to answer that question, right? We're going back to answer the question. No, I am doing the same direction, right? Did you see? I'm trying to use the same one that you have in the note.
right. I go.
Alright. Make sure we have all the right? And let's assume the length is L, right?
But I wanna I do twice.
Alright, let's go now. Probably about anything out there, right? In the come value say, right? But let's go. So here's what we want to get. We want to get the force on X. I just find force again. F is equal to what? VIL. That's okay? Assuming that theta is 90 degrees. Right. Nice. So current this way and the force this way, so they're at 90, right? Question. The force on X is BIL, right? So the force on X, we know what I is I1. We know the length is L. But what is B? What is causing the force on X?
Why?
The force on X is the magnetic field strength here. Right? So because of the magnetic field here, it's causing a force here. Yeah? So the force on X is dependent on the magnetic field strength at Y. That's okay? magnetic field strength at Y, the current in I, the current in I1, and the length. They both have the same length. Both conductors are the same length, right? And they have currents I1 and I2 flowing in them. Hold on. Right? How do we find By? What is the magnetic field strength? What's the magnetic flux density or magnetic field strength of Y?
I over
So it's mu naught I what?
I two
I2 over
by
2 pi by the separation between them, which is A. So if I take this formula and drop it in here, it will be the force on X is equal to mu naught I1 L. Sorry. I'm gonna drop in everything one time for you, right? By is mu naught I2 over 2 pi A, that's Px, multiplied by I1 L.
to the magnetic flux density.
You're okay with that? The magnetic flux density that causes the force on X is due to Y. Everybody okay with that? Yeah? So Faith, since you're communicating there, communicate with me and tell me what do you think would be the force on Y? Bx I by L. So Fy is what? Let's put it all together for now. Well, do I form By for you here, or will you find Bx and I put it together? Mu naught I, mu naught here, by I1, I2, L, all over. Same thing, right? Look at these two formulas here. What you notice is better, right? And its similarity is what?
Similarity, no.
Not much, so you need to
What is X? What is Y?
one is X and one is Y. But what you recognize about the formula? Identical.
That's similar.
So it means that Fx is equal to Fy. So when current in the same direction, the forces are what?
Attract.
Forces are attractive. They're equal. Yeah, yes. Right. Do me a favor now. Change directions and let's see what will change.
That's all it says. Oh, no.
I hate them. What we go, no one What is that?
But it's not really, that's the one, so. I can do the other door. So, yeah. 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 It's even like,
Sorry. So when you did the proof,
We see that FX equal negative FY
right? Why?
because of the formula.
Well, what is the formula make one positive and one negative?
And current.
Current. One going one way, one going the next way, so one will be positive, one will be negative.
I really do, right?
Nah,
No.
somewhere. Alright, nice.
Come on, you put down notes.
In the notes, boy.
In not any notes. I check the notes. Show me any notes like this.
That's not it. Just tell you what. Right?
They want love. So you do it in the abstract, you know?
Just put one negative, I thought.
No.
One positive, one negative. That's it. Everything else is the same. Right? Just put I1, well, I1 positive, I2 negative.
Why I don't, I'm sure you.
But it don't matter. You can switch it out. Alright, that is your first part.
So negative, let's get the.
Negative sign when it is culture. Equal would be positive is in the same direction.
This is supposed to be yours. No, we're around here. It's in here.
Only remember to sign up for the crash course.
So, when I make money, I say thank you. I said you thank you. Yeah. No, not this way.
So you took the trees off.
Yes, sir.
In bad yet, one bad out.
I am for sure.
Unless one bad. Alright, yes, no, I think I just showed you a question, but I lost it for you. You follow what they asking here?
You know, it's the kind of bump.
Christiana, you follow what to do here? I don't know why I can't zoom yet, but. No, can you show this relationship here? What I do on the board? To make sure you know what I do on the board. Right, the part underneath, I'll show you that next, right?
Yeah,
Right. You all might have to go back to one of the. Go back to this question from the place we did it a while ago and put it, get back the values, right? Watch it. Huh? Yeah, can I show you now? It was a question on drift velocity. No, you don't have to. There was a part D I did not do. So go back to your drift velocity question. Right, see if you remember this now. It was drift velocity and resistivity. Right, go back to this now because you need the values. Right, we did this in class. Right, go back to the values now, please. Yeah, you have the length of the wire, you have the resistivity, and maybe you find current and the length of wire. Oh, you have it?
Yeah.
Right? And then after that, I think I asked for,
Yeah.
right, after you have to find drift velocity. So using those values now, find part D. The average force experienced by each electron and the total force. We have to go back.
I want to say if you value stuff like F is on Q. That I was.
You don't have to go that if I just use them back this. What was the drift velocity? What was the drift velocity that we found?
I'm not seeing it.
Kiran. What was the drift velocity that we found in that question? Otherwise, go back and work it out. Yeah, well, yeah. What was the drift velocity? Back here. What I get the drift velocity in that question?
Yeah, it's not showing. It's not constant.
Anybody who can. Yeah, what's your velocity? That's part C. 8 by 10 to the. Alright, we'll use that, right? Yeah, that was like 2 or 3 weeks ago. So how we getting the force X? So now they have a wire at right angles. Calculate the average force experienced by each electron. How are you doing that? What's the formula we're going to use here?
Forces are divided by.
No, they say find the average force first, then the total.
What question?
Don't worry, you don't need anything else. Everything we're right here on the screen. How you find it? How you find F for you?
I mean, these
Huh? F is the force exerted on the electron.
right?
That's a formula that we did today. F is equal to
VQV.
right VQP.
Yeah.
Right, they gave us P.
You do that today?
Yes.
It's an electron, right?
Yeah.
So you charge by electron is
1.6 8 negative. Take one.
and what's the velocity is moving with?
8 times 10 to negative.
8 to the negative minus 30.
How is that the velocity? The drift velocity?
Huh?
How is that?
That's the average velocity of all the electron.
Yeah, but that'll get it wrong.
I don't know if you had picked it or something, but I was about that again.
That could. I probably.
Right, so use it. So too bad, use it. 8 by 10 to the minus 30. How much is that we get?
I don't need your own value.
Well, we have to use it. We
You
have
know,
to
it's not gonna get
force. A small force.
one positive.
Well, again, just multiply this out now,
I
please.
don't know what question.
Multiply this out.
More calculator, I don't know.
I don't know.
I want you.
Say, got 1.92 by 10 to the negative 50.
1 point.
92 by 10 to the negative 50. Newtons.
And then how we going, remember we want to check back that V value, right? But we're using that for today. How we getting the total force now?
Yeah, then multiply by the electron number.
We have bad boys about
What's the number of electrons?
9 by 10 to 28.
Right, so 9 by 10 to the 28 by
Oh, 4 seconds. Second.
machine.
No, you're strong. Very similar on the barriers.
Serious anyone?
5,000.
Each year.
Yeah. Easy
So
old
go
one.
on, curious to have observation from 5.6. So it's been with you as an area.
17 look.
You're on 17, no?
He was 17 look.
What's that?
Oh, 16, no?
Yeah, sure.
What's the
Low means under 30 seconds.
So that's slow, right? You can't figure out what 17 no be.
So you play 17.
Yeah, I'm gonna get you out that. I'm getting it right.
Oh.
What's up? Serious, then, right?
No.
Oh, that. Oh.
I just see this. I'll come like I going on the RET.
So why you can't?
On the RET.
No, keep on the. Keep on the street, yes, for the.
The reason why I didn't do this time is this. Yes, and that's not good. I guess 0.1728.
0.1728 Newton.
By 10 to the minus 20 something.
That's 28 and minus 30.
Right, by
Oh, sure, that's minus 30. I read the wrong thing, it's minus 50.
yeah, so it's by 10 to the minus 28. So 1.728 by 10 to the minus 25.
By 10 to the minus.
29.
Right, but that's on and off one.
Yeah,
Yeah, I told you to check by that velocity value.
because there's no way to beat them with the
It'll be so slow, it'll be faster than that.
Yeah.
Number.
Yes.
Like positive 5 and so. Alright, next one. Let's try this last one here. Last question. This one has to do with what we just had on board. So hopefully Cristiano will this one out for us. Right, take a read. You'll need to draw a diagram, right?
Huh?
We in between. Where people be.
Right, yes.
Oh, yeah.
Where PB? P will be somewhere in between, right?
Yeah.
But where would it be? Exactly in the middle, 235.
10 centimeters.
So who will have the stronger magnetic field? 5 or 10?
Caused by the ratio.
Who will have a stronger magnetic field? 5 or 10?
10.
10.
So therefore the force will be pushed a little closer
The
to
5.
5.
So it's like a 15.
Right? So you could call here X
Now more like
and what you will call the next side.
four.
No, to be exact. 5 to P is X. So P to 10 is what?
Why?
Alright, we want one variable alone.
2x, 2x, 2x.
The whole distance is 20, right?
Yeah.
So the part X and X part is what?
2x.
20 centimeters minus that. X is 5. 15 is the remainder.
Yeah, but we don't know 15 is no.
Exactly, it's correct.
You're right, you're right.
Right, now see if that will help you find exactly where P is. So what will be equal at those points earlier? And
The force.
not the force, well, B1 will be equal to B2 at that point.
Yeah.
Because they want where the magnetic field is 0. So at that point, B1 and B2 are equal. So see if we can find B1, see if we can find B2, things will cancel off and work it out fast. Oh, yeah, Yash, I see what you got.
Yeah.
Yash, you done? What you got? Oh, you got that. Somebody working without looking at your phone. Somebody working. Yeah. Right? What we have. So how do we find magnetic flux density for a straight wire?
Mu naught by the current over 2
Mu naught by the current over
2 pi by the distance.
by the distance. Very good. So it will be mu naught by 5. It don't really matter if it's 5 or 10, right? But mu naught by 5.
This is equal.
Yeah, because they equal. 2 pi by, let's say, is
Not 2 by 10. Oh, that approximate.
right. 2 pi by 5, right? I finish in 2 minutes.
5 minutes.
Yeah, 5 minutes. Who turns up? Who's the parent? Right? Here will be x. Next side will be mu naught 10 over 2 pi 20 minus x. Follow up, Joshua. Right? So I found the magnetic field strength due to the first wire, magnetic field strength to the second wire. Mu naught by 5, and the mu naught will cancel, 2 pi will cancel, and then we cross multiply. You will get 10x is equal to 5 by 20 minus X. Then you solve for X. Right? I have 5X is 100. Sorry, 15X is 100. X is 100 over 50. That'll be centimeters over there. What is that? 6 point something? All right. Right, next week we'll finish up magnets, right?
Yes, they are.
Ian guess, he put it in chat.
No, I guess the because I just use.
Oh, you look at the 50 to 5 to 10 ratio.
Yeah.
I don't 9. You have to log out.